Very nice. Then welcome to my presentation. I'm Christoph. I'm a master's student at the software architecture group at the Hasso-Plattner Institute in Germany. And yes, welcome to the paper. Let me start with a short motivation. We are talking about exploratory programming systems. So we are talking about programmers who are exploring running systems by their space and by their time. So they are asking different questions such as, what does the state of an object look like? What is an object currently doing? What has it been doing in the past? Or also, why does the variable or the value of this variable have changed in the past? And to answer this question, programmers can use different tools and workflows. For spatial questions that relate to the state of the system, they can use typically inspection tools. For temporal questions that are about the behavior of a program, they can use debugging tools or also omniscient debugging tools that allow programmers even to go back in time to explore the historic program behavior. But it already brings a challenge to programmers as they have to choose between different tools and they also have to switch between these tools. And especially for omniscient debuggers, this is a decision that also has to be made in advance, because if I do not use an omniscient debugger in the first place, then I am not able to go back in history at a later point in time. So these are some challenges to programmers, and this also leads us to our research question, which is how can we design tools for program exploration that supports both space-related and time-related questions, and that thus combine historical information about the program execution in a single workflow. And to answer this question, we make three contributions. We propose a universal tracing mode that makes it possible for exploratory programming systems always to have the historical information about the program execution available. We propose a space-time exploration model that brings together object inspection and debugging in a single workflow. And finally, we apply these concepts in our prototype, which we call the space-time inspector. But before we can get started, I also need to introduce some background to you. The first part is exploratory programming, which I already mentioned before. In general, this means we are working on a software system where the system or the requirements are not yet fully understood. And so programmers are working with a lot of trial and error to figure things out. And this also involves asking a lot of questions. And these questions can relate to the space of a system. So programmers ask questions about the state of the system, about the meaning and structure of data. But these questions can also refer to the time, to the behavior of the system. If programmers want to learn how something is working under the hood, or also how data is constructed and manipulated. And then we have object-oriented programming systems, which is just one application of exploratory programming, but in this case, everything is an object. Objects communicate with each other to form large systems. And importantly, programmers can access and manipulate all objects in the system while the program is running to explore and change the program. And one example, one application of object-oriented programming system is Squeak Smalltalk, which is also the system that we used for our prototype. And another important theory for us is the experience of immediacy, which has been proposed by David Unger and others already 20 years ago, but this is still relevant for us. So we have three dimensions of immediacy here that should be reduced, or that should be maximized as much as possible to increase the experience of immediacy. And the first dimension here is the temporal immediacy, which basically means if we want to enable users to recognize causality, then we need to avoid or reduce delays between an interaction and the response by the system. And then we have the spatial immediacy, which tells us basically that we should minimize the physical distance between things or events that belong together. And also the semantic immediacy is important, which generally means that we should minimize the conceptual distance. So for instance, we should try to avoid different representations of the same artifacts if possible. And then we have different program exploration tools, which usually, at least to some degree, adhere to these principles of immediacy. And we have object inspection tools here, which can be used to explore the state of a system. So we have different representations here, but usually we have something like a property sheet or also like a domain-specific visualization. And on the other hand, for exploring the behavior or the time of a program, we have debugging tools where we can execute a program step by step, and also omniscient debugging tools which record a trace of the program, which can then be explored independently of the original execution order, and where we also can use different means for navigation, such as events or changes to states and so on. But then we can also localize these different tools in this coordinate system of time and space. And there we can see that inspection tools typically only display an object at a single point in time, so they are constrained to the spatial dimension. And on the other hand, debugging tools are time-centric, but they only give us access to a small portion of the state which is relevant to the current method execution. So they are both limited in different ways. And in the background, you can see our version of a space-time exploration tool that brings together both dimensions within a single workflow. But to achieve this, we have to face the different challenges of immediacy. So the temporal immediacy is a problem mainly because omniscient debugging is technically slower than normal debugging. And if I decide later to use an omniscient debugger, I need to start all over the program execution. Spatial immediacy and semantic immediacy are also problems because the different tools which we have with inspectors and debuggers are not related to each other. They are different tools which we need to switch between, which use different representations. And to solve these problems, our universal tracing mode aims to avoid the first two kinds of immediacies because we can make the historical information available at all at once so that there is no technical overhead anymore. And with the space-time exploration model, we also avoid the overhead of switching between different tools. So let me start with the first contribution, the universal tracing mode. And here the main problem, as I already mentioned, is that there is a technical overhead of program tracers, which is required for omniscient debugging. And so here we collect three strategies that are helpful to avoiding or minimizing this overhead. The first one of them is the efficient trace model. So many program tracers actually create a full snapshot of the memory, of the entire memory at each point in time, which is obviously inefficient. And so what we instead suggest is that we detect fine-grained side effects in the bytecode and store the previous values as only when they are changed. And this massively can reduce the memory consumption and also provides an efficient access to read and append operations in the data structure, which is basically a map of sparse collections. The second strategy are explicit exploratory interfaces. Here the observation is that in many cases we have large systems where a lot of things are going on at the same time, but only a small part of this behavior is actually relevant. So for instance, we might have a graphical user interface with different objects representing the widgets on the screen, and each of these objects has one responsibility for rendering itself onto the screen and another one for reacting to user events. And in many situations, the programmer might just be interested in debugging and exploring these user interactions, but not in the rendering logic. And so here our idea is that we define system boundaries, and whenever these boundaries are crossed, then we enable or disable the program tracers. Some example of such explicit exploratory interfaces include the accesses to a model in an MVC application or also custom expression evaluations in an exploratory programming system. And so we can avoid tracing a large irrelevant portion of the program trace. And the last strategy, which also is an option, is program reproduction. And so actually some omniscient debuggers do not create a trace of the program at all, but just rerun the program on demand many times to collect further information as requested. But this requires, first of all, reproducible entry points, and second, also deterministic behavior of the program. The first requirement can, with some effort, be achieved. So we could, for instance, log all invocations of our explicit exploratory interfaces. And in many situations, there are also existing log sources available, such as the command history in a verbal. On the other hand, deterministic behavior is harder to achieve. In many situations, there could just be any kind of global state in the system that might affect the behavior of the program. And so we recommend to developers to use heuristics to detect such deviations and ask programmers how to proceed. But in general, we also recommend that we should try to prioritize upfront tracing over program reproduction to avoid this challenge at all. Alright, so that was the first contribution, which allows us to always have the historical information available, but then we still need to find a way to allow programmers to explore these collected data at once in a single workflow and tool. And this is our second contribution, the space-time exploration model. And here we start with something like a spatial view on an object, which could be something like a property sheet or a domain-specific visualization. And we combine that with another view, a temporal view that displays us a call tree, a time slider, or anything else. And both views refer to an object and to a program trace. And we can combine them in a single tool, which we here call the spacetime inspector, and which allows programmers to interact the system and explore it by both dimensions on par. And importantly, both dimensions are linked to each other, both views are linked to each other. So the programmer could select a portion of the state in the spatial view, and this selection will then influence the granularity of the temporal view. What does this mean? For instance, I could select a single variable in the spatial view, and in turn, this will make it unnecessary to display the entire call tree, and we only need to display a small subset, a small slice of the call tree, which only contains Z methods that are relevant for changing the value of the variable. This also works in the other direction. If the programmer selects a slice, so a subset of the time, then this selection will influence the informational density of the spatial view, so that we do not display the entire history of the state, but only the history within the selected time slice. And because this is pretty abstract, I'd like to give you a concrete example of this, and I would like to show you our prototype, the space-time inspector in Squeak Smalltalk. And the example which I would like to present to you is a runaway. A runaway is a class in Squeak which represents a sparse collection object. And now we would like to find out together how this class is implemented, how it is internally structured, and how we can use it and how it implements an addition operation. For that, I have a very small program here in Squeak which basically creates a new runaway and adds different values with different numbers of operands. And I can run this program here, which will automatically trace everything in this so-called omniscient workspace. And finally, I can explore my constructed runaway object in an omniscient inspector. And this gives me this view where we see on the left the temporal view and on the right the spatial view. And at the moment you can note that the temporal and the spatial granularity are very low. And I can change that by expanding the spatial view on the right, which then gives me an overview of the different properties of the different items in the runaway. So we can see the first item was present in this interval, the second one in this interval. And here we can also see that the interval or the length of this value has changed over time due to different addition operations. And so we also have these inline summaries here. And I can also select a single point in time to explore the state of the object at the single point in time. I can also use this time slider on the bottom to travel through the history of this object. But this is just a snapshot of the object for the now, or whether this only gives me a high-level overview of the object. If I'm actually interested in its internal structure, then I can choose a different representation, and instead of exploring the items, I can also explore the instance variables of this object. So in this spatial view, I now can see that the object consists of 5 different instances variables, 3 of them are none or null, and the 2 others are different arrays which have been reassigned multiple times, as we can see. And again, I can display the values at a single point in time. I can also expand this here to watch the different items in the array and scan into the object tree. And yes, and another feature which also exists is this blame feature here, so I can select a single variable and then all method invocations on the left will be highlighted that have changed this value, and thus this also allows me to further slice or drill down the different context trees for different states. So in general, what you can see from this example is that space-time exploration allows us to explore an object by its evolution and by its internal structure at once to figure out how certain operations are implemented. And how this works under the hood is that the space-time inspector is a small framework which combines different spatial and temporal views and synchronizes the selections with regard to time and space with each other. And this is actually a pretty generic model, so we can also use this for any kind of other models, of other views. And for this, I have a second demonstration for you where we are going to explore how regular expression matcher in Squeak works. And for this, we can combine different domain-specific views that already exist And this is how this looks like. So the first view is pretty simple. This is a string here on the top, which displays the input string we are trying to match with our regular expression matcher. The second one is a graphical representation of the NFA, the automaton which is used inside the matcher. So we see the different states and the connections here. And the third one is a temporal view. This is this blue line in the foreground, which displays the call stack, which is mapped onto this automaton. And so by combining these views, we can display the current state of the matcher here. We can see that the matcher is currently scanning into this automaton that is currently trying to match the first character of the string. And if we go forward in time, then we can see that the match is rejected because no underscore was found as accepted. But in the end, we also can find a complete match with a much deeper call stack. And the takeaway of this demo is just that we can build new space-time exploration tools by combining different space-time agnostic views. All right, so much for the demonstrations. Now I'd like to briefly talk about the evaluation of our ideas, and we start with the tracing. In general, we have to note that for our selected programs, we can indeed see a huge runtime overhead with this because our program tracer is not yet fully optimized, but still the absolute numbers are pretty small in most situations thanks to the explicit exploratory interfaces. And also the historic memory, which is incremental, allows us to maintain a very low memory footprint. And in general, we can say that the universal tracing is responsive at least up to medium-sized workloads. With regard to the space-time exploration, we have measured the delays for different navigation operations in our prototype, and we can here see that the temporal navigation was responsive for all considered use cases, while for spatial navigation and also the inline summaries that we have seen in the first demo, the temporal granularity matters indeed, and for larger workloads, there might still be noticeable delays, but it is important to note here that there are no domain-specific optimizations that have a lot of potential. For instance, our regular expression visualization, which has a pretty large temporal granularity, only took us about 2 seconds to compute because we made manual optimizations such as manually accessing the call tree and others. And then we can conclude with a discussion, first of all, about the programming experience. So we could streamline the model for program exploration by allowing programmers to answer questions that relate to both the space and the time of the system within a consolidated tool. This reduces the gulf of execution for programmers and also allows them to reflect on their own understanding of the system using a more consolidated vocabulary. So also we reduce interruptions and thus increase the experience of immediacy. And something which I also found very interesting is that we can provide programmers with richer contextual information using space-time exploration. So if I only am interested in learning about the structure of this object, just for free by accident, I also can learn something about the evolution of the state. And in many situations, it can improve my understanding of the semantics of the single variables. Also, there is an impact on tool building through space-time exploration. So through this framework, we can reuse existing space-time agnostic tools and combine them into new space-time exploration tools. And still there are some challenges. There is still an intrinsic complexity of tool building, or in many systems, not many views are available initially. And programmers are still required to make their views space-time aware if they want to use advanced space-time exploration features such as inline summaries, or also if they want to scale them up for larger workloads with manual optimizations. And also, finally, I'd like to share some interesting questions for future work with you. The first of them is, how can we integrate data flow into the space-time exploration model? At the moment, our notion of time in the model just refers to the evolution of state, but in many situations, the origin of state of values is also interesting if they want to if they want to find the cause of a bug or something like that. And another question of ours is, how can we use space-time exploration as an overarching concept for all kinds of exploratory programming activities? So at the moment, we have combined object inspection and debugging, but we could build further features such as allowing programmers to dynamically compose different views in the inspector, or to filter the system by the space and by the time. And eventually we could even express an entire symbolic debugger or omniscient debugger just as a composition or as a combination of different space-time views, and such make the make the information about the history, about the time of programs even more omnipresent in the entire debugging or exploratory programming session. So finally, let me conclude. In our paper, we have taken a look at how we can make object exploration tools aware of the temporal dimension of programs, and for this we have made 3 contributions. The first one is the practical universal tracing mode, which this is an efficient trace model, explicit exploratory interfaces in program reproduction to always have the historical information available in the system. We allow programmers to explore the system by both dimensions on par at once using the space-time exploration model, and we tested out these ideas using our prototype in Squeak. We found out that the performance was usually already promising, but yet for larger workloads, the spatial navigation still requires domain-specific optimizations. And with regard to the programming experience, we found out that we could streamline the program exploration model and provide programmers with richer contextual information, and also were able to build a framework that allows tool developers to combine existing domain-specific views to build new space-time exploration tools. And with that, I thank you a lot for your attention and looking forward to any questions, which you also can ask in the Discord channel later. Thank you.
Thank you very much, Christoph. Are there questions?
Hi there. Thanks for the talk and the interesting work. So I'm interested in the principles behind the visualization, but and the interaction. But what I'm specifically interested in here is how much that kind of a system's availability might affect the design of the actual program. Whether being familiar with how you can explore it after the fact might change the way you program it in the first place. So my specific question is that when you showed the examples there, when you made those examples, did you take code that was already written beforehand, or were you thinking about how it was going to look in your system when you wrote the code for the examples?
Yeah, thank you for the question. I would say it is a combination of both. So the first example, which was very simple example, was just assembled for this demonstration. But the second example was a real system in Squeak, which we did, which was already existing beforehand. So it was not tailored to this kind of exploration. But in general, we also found out that it is easier for space-time exploration if we use a lot of intrinsic states. So data flow is something which is not covered by our model. So if we have a program or an architecture where you are using a lot of functional behavior, a lot of extrinsic states that they are passing from one object to another, then this is something that we cannot cover with space-time exploration. And so systems that use side effects are definitely better suited for this kind of exploration.
Right. So potentially a different style of programming might make this kind of tool more effective.
Yes, I think you could say so, but side effect programming is already is a popular style, I think.
Okay. Thanks.
There's time for another question.
Hi, thank you for your talk. Very interesting. Maybe this style of programming could be live programming. I was wondering, though, about how you propose tracing the historical information. That do you represent the changes explicitly, or do you suggest capturing snapshots of the states? This might impact the amount of memory you use as well in your experiment. So I'm curious what the data structure should be and how they support the different features of omniscient debugging.
Yes, I will just back to the relevant slide. Where is the slide? Yes. Generally, we store or each variable in the system. We have a separate collection of values that have been changed. So, for instance, if this variable color here, or if the variable submove here is changed, then we store the previous value, and we do this again when every time a new value is assigned to the variable, we preserve the previous value in this data structure. And this means that we do not store any redundant values. But this is not a differential memory, if that was a question. So every assignment will store the entire value. If we have a string and add another character, we will still write out the entire string at each chance. So I'm not sure whether this answers the question.
Yes, thank you.
Final question. Then let's thank Christoph again.
Thank you.